It's a pleasure to introduce our first of two invited University of Maine alumni lectures, which we've been doing, for the past several years, at least. Pleasure to introduce Bonnie Newsom. Bonnie is a member of the Penobscot Nation and president of Talcott Consulting. She's also a PhD candidate in anthropology at the University of Massachusetts, Amherst. Bonnie got her master's degree here at the Institute, working with Dave Sanger back in 1999. And in the 10 years after that, she served as the Tribal Historic Preservation Officer for the Penobscot Nation. And I know on her list here, she's got some really interesting other affiliations. She serves as the chair of the Smithsonian's Reputation Review Committee and is also a member of NOAA's Marine Protected Areas Cultural Resources Working Group. And she's also the first Penobscot woman to be appointed as a trustee in the University of Maine system. So, great. Welcome, Bonnie. Thank you.
Well, thank you. Is this working okay? Is the mic working okay? Can everybody hear me? It's good to be here, and I really appreciate the invitation to participate in this year's symposium. Today, I'll be sharing my dissertation research with you, which examines technological choices made by potters living in the Penobscot River drainage area between roughly 3,000 and 500 years ago. First, I'll present the research context, and then I'll discuss my analytical methods, and finally, I'll share with you some very preliminary results of my analysis. In Maine, the prevailing archaeological model is for the ceramic period, which is 3,000 to roughly 500 years ago. The prevailing model for settlement patterns is one in which people organize themselves into two distinct populations inhabiting the interior and coast respectively. This two-population hypothesis was introduced by Sanger based on subsistence, seasonality, and site location data collected over the course of 2 decades of archaeological research on Maine's coastal shell middens. Archaeological evidence indicates that native people occupied coastal sites during multiple seasons of the year. And this challenged Snow's assertion that the early historical settlement pattern of people summering on the coast and wintering on the interior was the indigenous settlement pattern prior to European contact. Support for the two-population hypothesis is also evident in archaeological data showing distinctions in coastal and interior cordage twist patterns among fiber perishables used in pottery manufacture. Fiber perishables are items that people make from plant and animal fibers, and these include things like basketry, netting, and cordage. At different times during the ceramic period, here in Maine, people used cordage in ceramic surface treatments during the manufacturing process. And this diagram shows that there are two directions in which cordage can be twisted. By taking impressions of ceramics that cordage has been used on, the direction in which that person twisted the cordage can be determined. And here's an example of what we refer to as S-twist cordage. And this piece is from a coastal site here in Maine. In the 1980s, Peterson and Hamilton identified coastal and interior patterns in fiber perishables used in the manufacture of Aboriginal ceramics in Maine and other parts of the Northeast. However, the patterns are not consistent through time. Specifically, in the early ceramic period, roughly 3,000 to 2,100 years ago, pots from interior sites showed a dominant characteristic of S-twist cordage, whereas Z-twist cordage dominated vessels from coastal sites. At roughly 2,100 years ago, people stopped using cordage on their pots, and however, they maintained many of the other characteristics of pottery manufacture. Then roughly 1,300 years ago, cordage use returns in pottery manufacture, and distinctions in the coastal and interior twist patterns reoccur. This led Peterson and Hamilton to suggest an in situ coastal and interior continuity of populations for roughly 2,000 years during the ceramic period. Finally, late in the ceramic period, the interior coastal cordage distinction disappears altogether, and the majority of cordage makers are twisting their cordage with a Z twist. Peterson interpreted these coastal and interior cordage twist patterns as reflective of distinct learning networks. Following Wisner, he classified them as a form of assertive style, which is personally based and carries information that supports individual identity. Identifying cordage twist patterns in the Northeast was an important contribution to regional archaeology and specifically the two-population model. While patterns in cordage twist may be indicative of social phenomena linked to identity, it's important to acknowledge that cordage twist is part of a suite of artifact variables resulting from a complex relationship between humans and their materiality. And two, there are only two viable choices in cordage twist direction, and multiple groups may twist their cordage the same way but distinguish themselves by other means. The study presented here aims to expand on this earlier research and test the two-population hypothesis by comparing ceramic assemblages from 3 sites located within the Penobscot River drainage area. The theoretical tools I've selected to inform the study include concepts of human agency and technological style or choice. Agency-centered approaches to archaeological inquiry are relatively new and have been used to counter archaeological approaches in which people's actions are determined solely by external forces such as economics or the environment. And I'm using Broomfield's definition of agency, which is the intentional choices made by men and women as they take action to realize their goals. And while there are multiple definitions of agency, this one emphasizes human choice and action, and both of which are pertinent to this study. The second theoretical tool I used in this study is the concept of technological style, which is the formal integration of the behaviors performed during the manufacture and use of material culture, which expresses social information. And this approach focuses on a combination of choices in the artifact production process. It also examines the choices that people make within the context of natural and social constraints. The archaeological sites chosen for this study are situated within the Penobscot River Valley in Maine, and this is Maine's largest river system. And for millennia, the Penobscot River has served as a major travel route and cultural resource for Indigenous people, and it continues to play an important role in the cultural lifeways of contemporary Penobscot people. Evidence of human occupation within the watershed dates back roughly 9,000 years, with ceramic period sites occurring in both coastal and interior settings. This region of Maine provides an ideal setting to test the two-population hypothesis because it encompasses multiple physiographic units within a single river system that extends from the interior to the coast. The data sets selected for the study consist of ceramic period pottery collections from 3 locales with 3 distinct ecological settings. The interior ceramic sample was drawn from an existing collection from several small sites clustered at the confluence of the Piscataquis and Penobscot rivers near Howland, Maine. These data were recovered during a cultural resources management project that was conducted as part of hydroelectric relicensing for the Howland Dam. Howland is roughly 60 kilometers north of the head of tide and is clearly distinguished as an interior location. In the ceramic period, the ceramic sample from Howland spans the early and middle ceramic periods. Ceramics from the Knox site were selected to serve as a coastal sample. The Knox site is a shell-midden site located on Pell Island in East Penobscot Bay, Maine. It was excavated as part of the University of Maine's Coastal Archaeology Survey in 1979. Occupation at the site spans much of the ceramic period, with period between 1600 and 1200 BP representing the most intense occupation of the site. The third assemblage is from the Eddington Bend site, and this is a large cemetery and habitation site on the Penobscot River in Eddington, Maine. The site is situated on a high terrace near the head of tide. It was selected for this study because it has a substantial ceramic period component and is situated in a boundary area between the coast and the interior. The head of tide is unique ecologically, and it represents the blending of coastal and interior settings. The ceramic assemblage from the Eddington Bend site includes over 11,000 ceramic shards, and the collection from the site served as the primary focus of my analysis. Ceramics from the site reflect occupation throughout most of the ceramic period, from roughly 3,000 to 500 BP, with a majority of shards falling within the middle ceramic period, 2150 to 950 BP. Collectively, these assemblages provided a solid data set to examine technological choices people made as part of the ceramic manufacturing process. The analytical methods I applied to this study emulate methodologies by Chilton in her analysis of Aboriginal ceramics in New England. And at the core of this approach is the concept of Champ operatoire, or the operational sequence relative to the manufacture and use of material culture. The analytical process I used in this study is an attribute analysis of technological choice that Chilton developed as part of her study on Iroquois and New England pots. An attribute analysis of technological choice is designed to identify variation and covariation within and between objects and not to formulate a typology. And you can see an attribute is smallest analytical unit, and we would consider temper, or the material that's added to clay as part of the manufacturing process. We would consider that an attribute. Whereas we might label a pot Vignette 1, which is characteristically fabric impressed on both the interior and exterior. And so that's kind of the difference between a typological assessment and an attribute analysis. Attributes represent one variable of a ceramic vessel, and they include things such as surface treatment, temper type, and rim shape. And this slide illustrates some of the attributes I analyzed relative to morphology and surface treatment of pots. And this pot is one from the Eddington Bend site. These are some ceramics from Eddington Bend and Howland. And the attributes I've outlined here include more of the paste consistency and choices people are making in terms of what they're doing with the paste. And you can see things like temper size and type, or grit size and type, paste consistency and temper density. The unit of analysis in this study is a vessel lot analysis. And this type of analysis was chosen over a shard analysis to reduce statistical misrepresentation of the assemblage and to allow for consistency in inter-site analytical comparisons. Rims were selected as the primary focus of the Eddington Bend assemblage because they provide a comprehensive data set that includes a suite of attributes reflecting choices within the realm of vessel morphology, decoration, and paste characteristics. So I have recently finished the attribute analysis and have started the process of identifying some trends in the data. Overall, the sample includes roughly 400 ceramic vessels comprised of approximately 4,700 ceramic shards. Eddington Bend is the largest assemblage, and this slide shows a breakdown of the ceramics by site. And you can see that the Knox site is a little small, and I think what I may do is go back and look at possibly another coastal collection to add to the data set. Early in the process, I spent some time in the SCM lab with Dr. Yates to identify temper types. And temper, again, is what potters add to the clay to improve working, drying, or firing properties of the vessel. And during that process, we noted the presence of hematite in one of the sherds from Eddington Bend. And during my analysis, I noticed it was occurring in a number of sherds at that site. So I decided to note its presence at other sites as well. And I broke it down into 3 categories based on whether or not if it was visible in the paste and present throughout the clay matrix, if it was present, perhaps a few flecks of temper, of hematite as part of the temper, or if it was not visible at all. And this chart shows the percentages of vessels falling into those categories. Around the world, hematite is commonly used as a coloring agent in pottery, but we have never identified it as such here, and I don't think that's what they're using it for, because we're seeing it as, we're not seeing it as being used to color the overall vessel. I think in this case, it may be more representative of either the source of the clay or what kind of temper they're using. For each vessel, I also recorded the density of the temper. Density of temper can affect the pot's mechanical strength as well as its thermal shock resistance. And this slide shows some of the temper. In one of the sherds, it's relatively dense. People choose how much temper to add to their clay based on its intended function or firing properties. On this slide, the light blue bars represent sparsely tempered vessels, and the dark blue is heavily tempered. And you can see that overall, people at Howland and Knox are making more densely tempered pots than people at Eddington Bend. And this may be reflective of how they're being used. Pots with heavy temper tend to carry with them more mechanical strength, whereas pots that are more sparsely tempered are better for firing or in cooking. Finally, I wanted to take a moment to address the issue of cordage twist. The sample does not include many corded vessels, but overall we see that the data from these 3 sites confirm the coastal interior twist trends of S at interior sites and Z at the coast. It's important to note that these are very preliminary trends in the data, and I share you're not to draw conclusions about whether or not the people at Howland and Eddington Bend and the Knox site are different groups, but more so to illustrate how we might look at pottery beyond cordage twist or decoration to interpret social organization or human behavior. Following, as I mentioned, I'm in the process of interpreting the analysis now. There are a couple other pieces of analysis that I need to complete. One is a residue analysis. Many ceramic sherds have residues that adhere to the rim or the interior of the vessel, and those residues can be tested to determine what people were eating. And so that would help inform why they're making the choices they are for particular pots. The other piece I hope to do is do some SCM analysis on the manufacturing scraps. Manufacturing scraps are little pieces of fired clay that are produced as part of the ceramic manufacturing process, and we have those from these sites. And if we can understand the properties of that clay specifically before it gets temper added and manipulated to become a vessel, then we may be able to see some distinctions in where they're getting the clay. But that's very preliminary. I would like to close with a quote from Dr. Wayne Dyer. And it's when you change the way you look at things, the things you look at change. And this study is an attempt to change the way we look at archaeological ceramics in Maine in order to humanize past peoples and acknowledge their that their choices are important when we attempt to interpret their materiality in the archaeological record. Thank you, and I'm happy to answer any questions that anyone may have. No questions? Okay.
You may have said, but I didn't catch it, the source of the clay itself. Have you identified sites where that clay has been found?
Well, what I think they're using is Presumpscot Formation. And so, and because it's perfect, essentially, for using as pottery clay. But I have not done any source work. I'm hoping that perhaps if we can do some SEM on the manufacturing scraps, we can look at some of the signatures there and see what they are actually using.
So to follow up on that, it would be interesting to know whether the clay is from the same source, the coastal versus the interior.
It would be.
Yeah.
Yes. Yeah. Yeah.
I was just kind of curious about how hand dominance affects cordage twists.
Yes. It does affect cordage twist. And I think when Peterson did his original analysis, he accounted for that. And given that, I think I don't know the percentage of left-handed versus right-handed, but I know that he took that into consideration, and it is a factor.
Okay.
Well, how could they know what percentage of people 1,000 years ago was left right-handed?
Or allowed to be.
I don't
And
know.
also-
I don't know. It
Also,
could,
if a left-handed person teaches someone else how to do it,
yes. The interesting thing about cordage twist is it's linked to muscle memory. And so once you start twisting your cordage, it's very difficult to change how you do that. However, I've read some literature that suggests that cordage twist and how people twist cordage may not be simply a function of how it works best for them, but there are actually taboos in some cultures for twisting cordage one way. But you'll also find that people will veer from those taboos or those patterns just to see what will happen, you know. So again, it's about choice, right? People make choices for a variety of reasons.
Is there a standard to today's cordage twists? You go to the hardware store.
Is there a standard to today's
Yeah,
cordage?
go today to and look.
You know, I don't know, Hal. I don't know that
Maybe.
I don't know that I've ever looked at contemporary cordage.
Might be interesting.
Yeah, it would be. Cordage twist is fascinating, but you have to remember too that what I'm seeing in the data are that people are twisting their cordage one way, but they're using a multitude of plies. You know, they could be using 4 strands or 3 strands in the cordage. So there's a lot going on in the cordage that we are not looking at archaeologically, and at least in this part, at least in Maine. So I think there's a lot of room for interpretation of human behavior if we look at cordage more closely. Yes.
My impression is that there was a lot of exchange between coastal groups and interior groups, and you know, I'm just wondering how distinct these populations are thought to have been.
Well, Sanger, when he outlined the two-population model, he suggested that coastal folks were living a semi-sedentary life. So, and that people were making a living off of the abundant fish resources that were, you know, in that area. And so I think it's a matter of partially looking at how people are using that space. Are they semi-sedentary? Are they more mobile? I did the analysis on the Howland stuff for my master's thesis. And what I noted in those collections is that, and I compared them to some others further down on the Penobscot, and what I noted was that it's quite variable up there in terms of the overall design elements that I was looking at. And I thought that perhaps what we're seeing is a more mobile, or a space that's reflecting more mobility among people than other places, such as in the Pushaw Stream area, where you get these little sites that are clustered kind of off the beaten path. So I think in terms of looking at distinctions in people, I know he wouldn't have said they were ethnic groups, because there is a lot of interaction, and ethnicity is very difficult to define in any time, in any space, right? So I think it's looking at how people are organizing themselves.
How about the evidence from seasonal indicators along the coast?
Yeah.
What does that show? Does that show that people were sedentary?
It shows that people were occupying coastal areas during multiple seasons. So, and interestingly, one of the things that I'm looking at is trying to determine whether or not making pottery is a summer activity, because we have manufacturing scraps from, I know at least Howland and Eddington Bend. I'm not sure if we have them at Knox yet. If people are making pots, I think it's kind of difficult to make pots in the winter, because you have to have fire and water, and it's messy, and so perhaps we can look to that to get to some seasonality indicators. It's very difficult on the interior to look at faunal remains for seasonality because the preservation is just so poor.
In the pot mixture for the shirts, is there any fibrous material inside?
No. What happens is that usually burns out or erodes over time, and so we do have pots that are shell tempered. And interestingly, the Knox site, which is a coastal site, there's no shell temper there, which is unusual. It's all quartz. Quartz is the primary temper at Knox, and we're seeing that people are using quartz abundantly at the other sites as well. But yeah, shell temper, we also get shell temper on the interior sites, particularly late in the ceramic period. Yes.
I'd read that in the Massachusetts Bay Area, at least, that many of the coastal peoples had more than one village location. They would live close to the sea at one point, and then at a different season at further in. Would that be consistent with essentially sedentary, even though it's two villages within one general area? Or is that what's going on in Maine as well?
Well, I know that accounts from Norwich Walk, the Jesuit accounts from Norwich Walk, Maine, they acknowledge that the native people would go to the coast twice a year, in different seasons, but they would come back. But that's contact period stuff too, yeah. So it's very difficult to sort that out. But I think the pots, if we can have some good identity signatures in the pots, we may be able to get at those questions that way.
All right, thank you, Bob. Okay, so the next or the second of our 2 invited alumni lectures is from Dr. Alan Wanamaker. I know many of you remember Al from his time here, but for those of you who have come more recently, you might not know him. Let me share some thoughts on Al. Good thoughts, all good thoughts. So Al came to us after getting his bachelor's and master's degree at UNH. He came here in 2002 to do his PhD in Earth Sciences. He graduated in 2007 after doing his dissertation work reconstructing paleoceanographic conditions in the Gulf of Maine. He then went over to do a postdoc in the UK, somewhat ironically at Bangor University, where he did a lot of work as part of the Millennium, the European Millennium Project, right? Looking at high-resolution climate reconstructions in the North Atlantic. So 2 years there, and then he accepted a tenure-track position at Iowa State University. I'm not even sure the date of that, but
2009.
Doesn't really matter because they just told him as of the past week that he got tenure. And we're celebrating with Al at 6 o'clock at the Black Bear Tap Room for his tenure decision. So I think he's going to tell us today about some of his ongoing work in the North Atlantic, which is really redefining how we look at the evolution of climate out there in the late Holocene. So, Al, real pleasure.
Okay, thank you very much, Carl, for that introduction. It's really great to be home. It's great to see many of you who have, etched memories in my mind being in graduate school and Steve Norton some years ago in a winter evening sent me an email, invited me to come up here, and I crossed paths with pretty much all of the faculty here at one point or another, and had a really great time and learned a lot while I was here, and now I'm in the middle of the country where there's an ocean below me and all the other oceans are equidistant away, so it's very convenient. Today I'm going to climb out of the ocean and talk a little bit about some work that we've been doing in Portugal, essentially investigating the state of the North Atlantic Oscillation during medieval times. And many of you in here have done a lot of work in medieval times in the Little Ice Age, and of course we know that the North Atlantic Oscillation is a major weather maker. And in this region, it's been called, not so accurately, but it's been called sort of the ENSO of the Atlantic, just so people understand what we're talking about, the scale of things. Now, this is the field site here in Portugal, and somewhere up in there, you've got to find it every time, is a very, very small cave opening, and it usually takes about 2 hours to find it. We now have it GPS so we can get there. But the person who took me in there, and I need to go back because this is all Ron Deniston's work at Cornell College, and he's the Speleothem guru, and he's very kindly brought me into this. And I'll mention a little bit about Dinah Thatcher here. She's the one doing all of the hard work, but I have gone here and climbed up here, and I went with Ron, and he's been there, but I found the cave opening. He was up on top somewhere. I mean, he was gone forever. Anyhow, we did get in there. And this is Diana here inside of the cave structure. And that's what she looks like in the field, and that's what she looks like in the lab. And she spends very little time in the field and a lot of time in the lab. And this is the Speleothem of interest today that we'll be talking a lot about. And this is work from Diana's master's thesis, and she's defending her work in a couple of weeks. So I'm here as a storyteller and just to relay what we're finding, but also to talk about the problem that I think exists with the current sort of popular NEO reconstruction, which I'll sort of dissect. Background and motivation. Well, the North Atlantic Oscillation is the pressure gradient between Iceland and the Azores. This influences the strength of the westerlies, has dramatic influence on climate, modulating hydroclimate, ocean circulation patterns. It's the dominant mode of climate in the North Atlantic sector. And so it's really important. And this is thought to be highly variable through time. And we don't have a very long, well, it is a fairly long instrumental series, but not before 1850 or so, and then we rely on reconstruction. So various reconstructions have sort of different stories to tell, if you will. And one of these reconstructions, the only one that goes back 1,000 years, is the True et al. Reconstruction that was published in Science in 2009. And on another note, most of the NEO reconstructions are precipitation based because the NEO has a real strong influence on precipitation patterns in Europe. And here's a schematic of what that looks like. So in a positive phase, the pressure gradient between Iceland and the Azores is strong relatively. And so you get a strong zonal flow. And this makes the region here in the south or along the Iberian Peninsula dry. And then to the north in the UK and over towards Scandinavia, generally wet. And when it's in a negative phase, the pressure gradient relaxes and you get a more meridional flow, and this area becomes dry and that region becomes wet. So it's a dipole and it flip-flops. And so that's why a lot of the reconstructions are based on precipitation. Okay, this is what the EOF looks like in spatial sense. Essentially, you're loading up the high pressures here and the low pressure there, and you can see right in the center of that is the Iberian Peninsula. So it's perhaps one of the most strategic locations you'd want to go to be under the influence of the dipole to the south. So in a NEO positive mode, there tends to be an increased strength in the westerly storm tracks, more to the north and wetter in northern Europe, dry in southern Europe. And the opposite is true in a minus mode. The westerlies are suppressed a bit. Storms are more southerly, and it's wetter in southern Europe and North Africa. And so we pretty much have a good idea of what we would think the precipitation effects in Portugal would be based on the NEO mode. Here's a time series of the NEO through time. And the thing that I want you to know is it's not really a multi-decadal pattern. It doesn't have periods where, at least in the instrumental period, it's in the same mode for 40, 50, or 60 years like the Atlantic multi-decadal oscillation. It's more variable. And this is really important because when we start talking about the True hypothesis, they're suggesting very much entrenched modes for centuries. Okay, so again, we're thinking about this flip-flopping of the moisture dynamics in that region. So what I want to do now is to look at the True reconstruction, and this came out of the Millennium Project. So I watched it go from the first couple of comparisons to a manuscript that was prepared for climate dynamics, and then they got a bit excited and they sent it off to Science, and it was published there, and it's become quite a popular reconstruction. So I know all of the co-authors, so I'm a little critical, I'm a lot critical, skeptical of this reconstruction, and they're friends of mine. So I don't want you to think that I'm being mean to them, but I know them all, and I voiced this with them. So I want to sort of dissect it for you. So the title really captures it: persistent positive North Atlantic oscillation mode, dominated medieval climate anomaly. And as I said, it's quite a popular paper. It's been cited over 400 times now since 2009. And there are some people who are really skeptical of it, but there are a lot of people who are now redefining their records based on the NEO being in a positive mode for 400 years. And I see that as a major problem. Okay, this is what the reconstruction looks like. It came about serendipitously because Jan Asper had a really good Moroccan tree record, so just south of the Iberian Peninsula in North Africa, and that's shown up here in sort of this reddish color. It's from a lot of tree rings, and I'll show you those data in a minute. Okay, so this is these trees are prone to stress related to drought, and so that's why there's a connection to those, and that makes sense. Okay, and in Scotland, there's one stalagmite record where they measured the lamina width. Okay, through a UV fluorescence, there's a little bit of organics that gets into the speleothem, and it has annual banding. And so they just measured them, okay? And that is in the northern node. And so what they saw was essentially, and these are in Z-scores just to normalize those data, that's how the authors presented it. And it's just a raw value minus the mean value divided by the standard deviation. It's just a way to normalize data. And so what they saw was an out of phase behavior from the Scotland record and the Moroccan record. And this is what you would expect based on the precipitation dynamics for that region. Okay, so they're opposite of one another. What I really want you to note, though, is here in medieval times especially, you can see that the Scotland record is largely invariant, okay, compared to the Moroccan record, which is, it certainly is lower here, but it has some pretty big variability in it. When these two were merged together, this is the reconstruction that came out of it. And the way it scaled is that during the entire medieval period, which was defined by these authors roughly, well, even before 1100, but to about 1450, was a positive mode. Never dipping below the 0. Okay, and these data are smooth. They're about a 30-year mean. Okay, and then you transition into the Little Ice Age somewhere in here, and it becomes a more variable NEO system, going between positive and negative, but maybe a little bit more variable. And so now people have really grabbed onto this idea that, oh, I don't have to worry about what the NA was doing in medieval times. It was always positive. And that's what I'd like to dissect. Okay, so this is the Moroccan record published by Jan Esper and colleagues. Here's a lot of data, okay? It comes from 164,000 annual increments from hundreds of trees. It's highly replicated. And as you go back in time, this is 2000 over here, this is 1100 over here. This is the reconstruction here. And generally speaking, when you're below this line, it's drier. So sure, it's drier in Morocco in medieval times, and it becomes wetter as you come into the modern period, for sure. I have no doubt about this record. However, the Moroccan record is situated on the edge of the NEO system. So the NEO is non-stationary. So as it moves through time, okay, like this perhaps, there's going to be times, maybe a little faster, there's going to be times where Morocco is going to be under that influence more or less. The Iberian Peninsula is directly in that zone. I would say better situated. But that's my only criticism of this, is so that this may not capture the non-stationary behavior of the NEO, but it's a huge amount of data. Okay, now contrast this to the northern node. Okay, Proctor and colleagues and Andy Baker is on the science paper. Okay, it's one stalagmite growth record, and the number, I took this out of the manuscript and it was small, but this is 900, 1400, 2000, and so there was a small accumulation of the speleothem here on the orders of 30 microns per year, and this is coincident with wet times, and then it increased through time. Okay, it began getting drier there. Now, one of the things that we would like to have is an ideal precipitation record. In other words, there's no temperature influence. Well, that's really hard because with hydroclimate, temperature and precipitation is often linked. And that is true for this record here. So first of all, they smoothed their data with a 10-year filter, and they compared their record to the NEO for a really long time, 1865 to 1990, and they had an inverse correlation, the R value of minus 0.7, but it was filtered with a 10-year, it was smoothed with a 10-year filter, so it has about 12 degrees of freedom, okay, and it is significant. But if you look at it, there's also an influence of temperature, okay, positively correlated with temperature. About 25% of the variance could be explained by that, and a slightly stronger inverse relationship with precipitation. So it's important to note that this Scottish record has an influence of temperature and precipitation embedded in it. But my main point is you're taking thousands of trees from Morocco and you're using one record from Scotland, not even two, just one. And that one is largely invariant. How many of you have been to Scotland? It's wet. It's like, it's wet, wet, wet. It doesn't get substantially wetter. I mean, if you spent any time there, it's really wet, okay? I don't know that it ever could get dry, but the point is that this is one cave, okay, in one location, and it's driving the reconstruction, okay? So I think there's something going on with the scaling of this reconstruction here. Okay, so yeah. Again, so this is what we're supposed to eat and say the NEO is in a persistent mode for 4 centuries. Yet we see nothing like that in the instrumental series, and modelers have a real hard time replicating a 400 persistence in the NAO mode. Okay, so this is where our study hopefully will come in and shed some light on this. So we're in Portugal, and this is Lisbon right down here, and we're working in this natural area here, and this is blown up. It's a limestone massif, and the cave is at about 450 meters above sea level. And again, on this geologic map, here's Lisbon right here, and the study site is over here. It's actually built from a mid-Jurassic limestone, and it was uplifted during late Cretaceous to Paleogene, and you know, probably beginning about 100 million years ago, where there was large tectonic uplift. And it's been associated with the Perrine orogeny, and then after it was uplifted, we started to develop the karst environment. And you can see there's all sorts of faulting going on in here, and there's a lot of faults which allow this block to essentially be lifted up. Okay, and so we also, before we get started, we wanted to look at what's influencing the isotopic composition of precipitation that's falling in this region. And we can go to the GNIP database, or the Global Network of Isotopes and Precipitation. And there were monthly averages from Lisbon, Portugal from 1989 to 2004. So not a terribly long time, despite Lisbon having this very, very long record of sea level pressure. And there is an effect on how much it rains. So when it rains more, okay, the isotopic values go lower. This is the amount effect in the speleothem literature, okay? And so the idea would be that when it rains a lot, the speleothems are on, and it's an on-off switch, okay? This is how it works in Australia and in monsoon locations, but we also have to consider the temperature effects, and there is a temperature effect. So when it's warmer out, the values actually go higher, okay? So there's gonna be 2 modulating effects here. The good news is that we can at least say, cooler, wetter, warmer, drier, and those 2 consistently will go together. Okay, so the goals and hypotheses of this work. Well, one is just to contribute to the understanding of hydroclimate and the winter North Atlantic oscillation behavior at the high pressure dipole in Portugal for recent millennia, really to test the hypothesis that Trouet and colleagues have put forth. We also want to evaluate the behavior, namely the persistence of the winter NEO during medieval times. In our hypothesis, our first one is that our stalagmite isotope record will reflect both precipitation dynamics and outside cave temperatures, okay? And so we will be able to relatively say if it's dry or warm or cool or wet. And hypothesis number 2 is that I bet that the NEO largely was in a positive mode in medieval times, but not for centuries at a time. It was likely more variable than that. Okay, and so here's a map showing the effect of the winter North Atlantic oscillation and precipitation in this region. And down here is a correlation continuum here. So this region is positively correlated with the winter NEO, and this is inversely correlated with the winter NEO. In Portugal, we have pronounced wet and dry seasons. In fact, if you do get rain in the summertime, it doesn't generally percolate very far into the soil. It gets utilized right away, or it's gone through evapotranspiration. Most people disregard any summer precipitation in this model. It's under the influence of the winter North Atlantic oscillation. There's a strong relationship with the WNAO, and 60 to 80% of winter precipitation can be explained by the winter NAO at our study site here in Portugal. Oddly enough, there are very, very, very few high resolution records coming out of Spain and Portugal. And not having been in the speleothem world for a really long time, I've talked to people at conferences and they said, well, people worry about the reproducibility of those records in this region. And so I've been keeping that in mind. Okay, and so moving on to the speleothems. So speleothems just broadly are talking about stalactites or stalagmites. The stalactites come down from the ceiling, okay, and right below them grow the stalagmites. We tend to use with the stalagmites because the drip geometry is a little bit better. This is an example of a stalagmite here, and you can see that the layers change a little bit through time, so we have to change our orientation when we sample them. And this is the speleothem that we actually gathered from this cave. It was way back. In fact, this room is about the size of the cave. It's about half as wide as this room, but it's about as far back as this room goes, but it keeps going down. And then about 20 feet up toward the ceiling, there's a loft. And that's where this was taken from. This one right here. And this is the same speleothem that has been sectioned. So speleothems are useful proxies. They have a wide geographic distribution. Well, you had to have a karst topography to start with, but there's a lot of that around. They can potentially be really long and continuous records, and we've seen some really great work come out of China. These really long records tell us a lot about climate variability on, sort of hundreds of thousands of years. We're able to accurately date them using uranium-thorium disequilibrium methods, and precipitation and temperature dynamics drive growth. So they are related to the rain. That's how they grow, okay? And I thought this would be appropriate. This is not my quote, but this is from Henderson. For paleoclimate, the past few decades have been the age of the ice core. The next two may be the age of the speleothem. So we will see. So first of all, this is not a funded project, and we're basically collecting data, and I'll be writing a proposal this fall. So we had to get over there and get some instruments into the cave so that when we end up with some data, we'll know what it means. So the other thing is that although there's precipitation records down in Lisbon, it's still 150 kilometers away and at sea level. So we looked for a weather station that was nearby and at the same elevation, Montreal, Portugal, 57 kilometers away. So we can look at precipitation from that location during this time period. So we've installed temperature and relative humidity instruments inside the cave and outside the cave. And whenever we go over there, we collect any water that's available. I went over last June, and in fact, it rained, and it had really high isotopic composition, about minus 1.5 per mil. And then Dinah went back in November, and it was about minus 6.5 per mil. And we've collected drip water coming down from the stalactites, and it's about minus 4.5 per mil when we were there. So it's definitely skewed in the winter precipitation value. And we installed. Right down here is where the speleothem was that we removed. And we installed the drip counter. So the stalactite that was feeding the speleothem that we've sampled now has a little drip counter on it. So when it's an acoustic type of a counter, so it falls on it and it records the drip. And so we can get to the hydrodynamics of the cave. Because when we went there, we didn't know how long the water took to get in there at all. These are the instruments down inside the cave measuring temperature, relative humidity, and those types of things. Okay, and so like Nina, we spend a lot of time sampling carbonates. One reason I like working on speleothems is it's carbonate. I understand carbonates. It's kind of the same system, but I just have to remember I'm not in the ocean. Okay, and so the same types of things that are driving the isotope, especially oxygen isotopes, in speleothem are similar to what we have to consider in seashells. Okay, these big holes here, that's where we sampled for uranium thorium dating, and we hand sampled this at low resolution to start with to see if there was a signal, to see if it was even worth pursuing. And when we realized there was, Diana got to work and milled this along this transect, and it took her probably continuously about 6 months to do that. So it takes off to a 200 micrometer swath each time it goes by, so we get 5 samples per millimeter. And that leads to a decadal to subdecadal resolution. And of course, we get both oxygen and carbon isotope measurements from each sample. Yeah, they spend a lot of time at this micro drill taking up tiny amounts of carbonate. I've run it, it's fun. Okay, so many of you know this very well. Just want to quickly go through the semantics. For any carbonate, okay, whether it's aragonite or calcite, and these are calcite, the delta 18O is a function of temperature of precipitation. Okay, that's really important. And then the isotopic composition of the water. Okay, and so to understand the climate data that we are hopefully deriving from these, we need to understand the causes of the calcite change. So the temperature at calcite formation, okay, we have to consider that. And we have to understand the water. So the precipitation amount, okay, that will, as we saw from the instrumental data, that will change the isotopic composition. And if the source is coming from, say, the Mediterranean versus the Atlantic, it will have a different signal. Just like in your ice cores, if your storm is coming from a different direction down in Antarctica, you might get a slightly different signal of the precipitation based on the source effect. So we need to understand that. Okay, and so we're going to sort of move down this path where we assume temperature inside the cave is constant or nearly constant or almost negligible. Okay, and I'll show you why in a couple of slides. So if we have drier conditions outside of the cave, okay, it's going to be coincident with generally warmer conditions. We're going to get more evaporation during the precipitation events, and this is going to drive the delta 18O of the precipitation and the drip water coming through the karst up. So we expect that the delta 18O of the calcite would go up. And conversely, under wetter and cooler conditions outside the cave, okay, we'd have less evaporation during precipitation, and the delta 18O of the precip and the drip water would go down. Therefore, the delta 18O of the calcite would go down. Carbon isotopes, those of you who work with them are always a little bit harder than oxygen isotopes, but you can imagine that temperature and the amount of precipitation falling through a soil profile above the cave is going to change the respiration in the soil and the microbial interactions. And so it wouldn't be surprising to see a coupling between temperature and precipitation on the carbon isotopes as well. But it's also a function of the isotopic composition of the limestone that it's going through. That's sort of mediating that signal. That's not really changing. So we're going to get a relative change in one direction or the other direction. That's probably more related to the temperature. And also over longer time periods, if we change our plant types, C3 to C4, okay, we would see then a change in the soil dissolved inorganic carbon pool. Okay, and so under these conditions, dry and warm, we would expect that the delta 13C of dissolved inorganic carbon drip water would go up, and the same thing would happen in the calcite. And during wet and cool cycles, we'd expect that the delta 13C of DIC to go down, and also in the calcite. Okay, so let's look at some of the instrumental data. When we installed the drip counter, we had a funnel under it, and so we're collecting that water. In our high-tech vials here, these are old soda cans all wired together, so we can get up to 6 liters of water until we get there next time, and then we can analyze that for all sorts of things, but certainly the isotopic composition. This is the precipitation at Mount Real and drip counts, okay? And so this is showing you that a lot of the precipitation is occurring in the fall or winter months, and not a lot is happening in the intervening summer. And so we installed this counter back here in June, and it started, and the cave is actively dripping, okay? And so that was interesting. But as the summer progressed, the number of drip counts went down, down to around 300 per day. And then we started to get the classic increase in precipitation in the fall into winter, and you see a dramatic response in the drip rate going up to about 800 per day. And I'm sure this is a lot higher now. We just haven't been back there to retrieve those data. And it appears that once the outside cave environment is saturated, you get a response in about 2 weeks, which is really great. And it also goes back to the point that if you do get some summertime precipitation, it's probably not penetrating down through that karst environment. Okay, it's staying in the soil zone and probably being evaporated away. Okay, and so outside cave, so orange is the cave temperature. So back here in August of 2013, it was about 25 degrees Celsius. It got down to about 8 degrees Celsius in about February, and then it climbed back up. Okay, and so it's a pretty large seasonal signal. Now you go into the cave, and you start off at about 14.5. It maximizes a little bit later. Okay, it's a delay, as you might expect. Okay, and it cools down to a whopping 13.9, and it slowly goes back up. So we have less than 1 degree of Celsius of change in the cave. And I know this is just 1 year. We'll know more when we go back. But it's a very small cave temperature. Relative humidity outside changes a lot. These are probably fronts moving through where you have sort of wetter periods and then drying going on. But inside the cave, with the exception of maybe this ventilation event, humidity, relative humidity inside the cave is 100%, which means we're not going to have evaporation of the drip water that's falling down, okay, because you're completely saturated. And so this looks like an ideal setting to sample speleothems from because it's so well behaved. We have 14 uranium thorium dates across that speleothem shown here. So this is distance from the top of the stalagmite. So going back 100 millimeters, we get to about 2,500 years before present. And you can see that these data are pretty well represented by just a linear fit, okay? And whether you use growth rates exactly between these areas or you use a linear fit, it pretty much gives you the same look and age model. Unfortunately, despite sampling the top a lot, we don't have a modern top. It stopped growing about 200 years ago. And we're not really sure why that happened, but there was the great earthquake of Lisbon at the end of the 1700s, and those dates sort of overlap. And a lot of these stalactites broke off apparently during this, and then soda straws have grown in their place. So we're going to try to date when those soda straws actually started to grow to see if, in fact, it was related to the earthquake. But nonetheless, if we're thinking about medieval climate, it should be okay to do this comparison. Okay, so here are the oxygen isotopes here in blue, coupled with the carbon isotopes in green. And this is calendar year, so this is the top here at about 1800, where it stopped growing. These are all the dates back through time. This is a low initial uranium cave, so that leads to somewhat large error bars. But we have a lot of dates along here. It's pretty common to only have 3 dates for a record this long, and we have 14. So we can move these around a little bit, but not outside of those error bars. And this will become important in a couple of minutes. So one thing that you see is that there's a lot of variability, and there's some rapid change inside of these speleothems. Notably, this is just a giant shift in the carbon isotopes here. It's interesting also because there's a lot of variance shared between carbon and oxygen isotopes. In fact, 38% not smoothing it. So it's for every sample there, no filter, they share about 38% of variance. So the idea that there's a temperature and precipitation control on both of those systems is the likely reason, but also you could have a vegetation signal that would also respond to temperature. It's a very scrubby, it's almost impossible to make it to the top of the cave, but it's really scrubby and it's brushy, and there's a moss layer that's on top of the ground, and it's real hummocky organic soil layer, not a very thick soil layer above the cave. Okay, so that's the whole record. And what I want to do is zoom in on the area of interest. And now, George, before you ask me why I put those markers there for the medieval climate anomaly in the Little Ice Age, it's only so that I can compare it to the dates that Trouet put there. Okay? Because we might want to.
Which dates?
The dates here for the medieval climate anomaly in the Little Ice Age. The last time I gave a talk here, I got in trouble from you for doing that. I remember that. Maybe you don't remember that. I remembered. But for comparison, okay, I put those there defined by the Trouet paper so that we can compare apples to apples. And so, generally speaking, though, dry and warm is up and wet and cool is down, okay, as I've identified along the way. As expected, there seems to be an insulation impact on these data. So over the entire Holocene, insulation has been decreasing. And if you look over the long-term record and you compare it to 40 degrees north insulation in summertime, there probably is what is driving that long-term trend. And we're not so interested in the long-term trend to answer this particular question. So we have just detrended the data to look at the sort of the centennial scale variability rather than the millennial scale variability. Okay, and so with those detrended data, we've just plotted it up against the Moberg Northern Hemisphere temperature anomaly data, and they're shown here in blue. They're continuous here, and the anomalies are here in degrees Celsius. My scale got cut off somehow, and it's referencing the mean Northern Hemisphere air temperatures from 1961 to 1990. Is Dan Belknap here? Dan Belknap would yell at me for just putting squigglies up here and not doing statistics on this. But you got to remember that on the speleothem data, you can move them around a little bit because we probably haven't captured the sedimentation rates perfectly between when we have the dates. The main point is that at the warmest time back around here, we also have values that are consistent in the isotopes with a warm, dry situation. And then here in the Little Ice Age, we also have these the values that are consistent with that. There does seem to be an imprint of temperature there, although we've not yet quantified it by binning the data into similar time slots, but we will do that. If we now go and look at the detrended data and we put up the medieval climate anomaly interval and the Little Ice Age interval, and we sort of go across here what seems to be about the mean or so in those data, and we just put our arrows up here and we say dry and warm is up and wet and cool is down, and we look at it, what we see is that for a good portion of the medieval climate anomaly, it in fact seems to be warm and dry, consistent with the Trouet model. However, right in the heart of the MCA, at least in the Iberian Peninsula in Portugal, by this one record, it's showing that it went into a mode that is more consistent with a NEO minus mode. And it popped back up, and then it largely went down into a wetter, cooler mode in the Little Ice Age, and it's come out into a drier and warmer mode now, which is expected with the instrumental record of the NAO. When you hang these two records together on the same graph, the NAO reconstruction by Trouet is here in green, and you can see that it's persistently positive for that entire 400 years. And here's our record here in black, and it's going along pretty nicely, but then it crashes down in here, and it comes back up, and there's some coherence there. Now, the point I want to make about the error bar is, even if I wanted to, and pull this all the way over to there, it's 2 times larger than the error bar. So I can't explain this happening, this big change here in the oxygen isotopes happening there as a result of, it's actually in the Little Ice Age. It's not, it's in the middle of the medieval climate anomaly. So we would have to then push all these dates around. So it's inconsistent with being an age error. Okay, so the people who have been trying to model this behavior haven't been able to reproduce a behavior that keeps the NEO in a positive state for 400 years. And our data does tend to show a more variable hydroclimate at that one location. Okay, now interestingly, I've mentioned Andy Baker. Well, he was a co-author with Proctor on the lamina width study. He recently published a paper on the same speleothem using oxygen isotopes. And in that paper, they argued that the oxygen isotopes from the speleothem was not being influenced by the North Atlantic Oscillation, which I thought was interesting. And so I figured, well, let's just plot them up, okay? Let's just test this little hypothesis, because now we have speleothem oxygen isotopes from the northern node and the southern node, and they should show out of phase behavior if they're influenced by a regional signal, right? And so here we have the Scotland one here, and the Portugal one here. And if you just look at the trend is that they're both moving in opposite directions during this time period, okay, and in this time period, and then they again move in opposite directions. And so they're showing this anti-phase behavior that is consistent with an NEO-like mechanism, yet they argue that their isotopes are not impacted by the NEO. And I'll let you read the paper if you want to get into the details of as why they think that is. But I thought that was really interesting because this is counter to the lamina width story. Okay, and so here's a comparison with a Spanish composite of 3 speleothems. So it's also very close by in the Iberian Peninsula. And those data are shown in red here, and ours are shown in black. And again, you can see there's a sampling resolution difference. Our record in red, the red record actually is a bit more resolved. But you generally see an increase in trend in this direction, a big change here, an increase here, another fall here, and then a steady increase there. And this, to me, when I saw these data, I got really excited. Not so much that what the carbon isotopes are telling me, it's just that it probably means that my speleothem that Diana has is not just our cave. It's not just our little crazy cave doing whatever it wants. It's matching another speleothem in a different part of the region showing a similar response. And it also means that my age model is probably pretty decent on here. You know, so these are all basically changing, the big changes at about the same time. Okay, so in summary, the coherence between the Spanish and the Portugal speleothem delta 13 values indicate a regional signal. In other words, it's not just our cave doing something funny, okay? It's another proxy record developed by other folks with their own age models and errors. And it makes me think that our age depth model is you know, pretty decent. The speleothems from our cave reflect hydroclimate, and this is the combined effects of both temperature and precipitation. And we have higher but variable delta 18O values within the medieval climate anomaly. And it indicates a positive NEO mode often, but not a persistent mode for centuries. And so that's the major finding of this work, is that it largely disagrees with the True model of a persistent NEO during the entire medieval climate anomaly. And so we have a lot of work to do. This is in fact preliminary data. So we want to install a MET station. We have to look at replicating our own data within our cave. We have other speleothems to do. I'll be doing some proposal writing to try to get money to go back there. And I can guarantee you that spring has sprung there. It's quite a beautiful place. And with that, I'll take any questions that you may have.
well, if the Speleothem stopped growing 200 years ago, how come they're still coming down?
Yeah, so there's also the saturation state that is required. It has to be super saturated. And so what we have to do is get a hold of fresh water the next time we're there and actually get the total alkalinity essentially of the water and the temperature in the cave, and then we can see if it's super saturated or not. So there could be something to do with that. Or we got there and there is a little bit of fine calcite in recent decades, say, but when you get these states, you need about 100 milligrams of carbonate powder to get a reliable date. And so we might be starting to get a modern top, but there's been a hiatus. So it's been dripping since we've been there, but that's only been a couple of years. It was really disappointing because, I mean, now TrueA can argue back to us and say, well, you haven't calibrated it. And they are absolutely right. But with that in mind, it's still Portugal, and it's either going to rain or not rain, and the stalagmites are going to grow or not grow, and the isotopes reflect that. So even though we can't perfectly calibrate it with the NEO, I think NEO is the main driver. Kirk?
How do you know there aren't other hiatuses in it?
Just
If
by,
there's one
yeah.
now, why wouldn't there be before?
Yep, so if you look at, let me go back here quite a bit. The age model doesn't really support a lot of hiatuses in there because we would then start to get really flat behavior in there. There could be some real small ones, but they certainly were persistent. Sharon?
When you compare the two speleothems and they both converged and then diverged,
Yes.
is there anything significant to that?
Well, yeah, because if the NEO was driving it, you would expect that they're going to have opposite behavior because it's both in the northern node and the southern node.
But they met at a point and then changed.
Right. One was showing drying while the other one was getting wetter, and then they went the opposite way again. And so that would be, I think, related to the change of the NEO system. Steve?
With your constant temperature and your 100% humidity, your precipitation has to be driven probably by degassing of CO2. As the vegetation changes on the surface, maybe you're getting changes in the CO2 pressure in the soil because of different kinds of respiration.
Right.
How would that translate down into your signals?
I mean,
through.
yeah, so it's going to modify the dissolved inorganic carbon of the water that's coming through, and that should be reflected in the carbon isotopes. And so those processes are also driven by temperature and precipitation dynamics, and that's why we think the oxygen and carbon isotopes are linked. But you're going to have, if you have vegetation shift between C3 or C4, you're going to see them move in the direction of those, and the value is actually being moderated by the rock, okay? But when it gets warmer and drier, it moves towards C4, and when it gets cooler and wetter, it moves towards C3. And so until we actually get in the soil and start making some measurements, the carbon isotopes doing anything useful is a bit of a surprise. I don't know, do you get 2 questions in this? Okay, go ahead.
As many as we want. We have extra time. Did you think about or look at any potential correlations between what's happening in the cave and with sea surface temperatures?
We will. We haven't yet. In the Scottish growth lamina width one, they have a very strong coupling with sea surface temperature. We haven't gone there yet with sea surface temperature off the Iberian Peninsula.
There's a lot of people are of the notion, scientists that is, are of the notion that sea surface temperature anomalies in the Atlantic and or in the Pacific are very much connected physically to drought and mega drought in North America, and I don't doubt that they would be in the European or Eurasian continent as well. In which case, those sea surface temperature anomalies don't really have very much to do with the NAO wouldn't come in that
Yeah.
particular case.
Yeah.
You could account for
Yep.
the dry and wetter just based on longer-term climate changes in the ocean system. So I would definitely be looking at that. The other-
Yeah, I mean, the good news is Diana's staying on for a PhD, so
There you go.
Yeah, we'll
Just
stop
like you
her
have
report.
Nina going
Yeah.
over there to keep
Yeah.
going your other stuff. Yeah.
absolutely. All right, go on.
Is it possible that the bulk of the response that you are looking at might be connected to simply the change in the size and magnitude and seasonality of the Hadley circulation, and that maybe the storms that track into Scotland and whatnot have their other interannual variability? I mean, if the position of the downward branch of the Hadley circulation in the Atlantic into Europe's sector were to just stay in more summer-like position in the medieval warm period, then you don't necessarily have to have the Icelandic low doing anything other than what it already does all the time. And I would suggest that that might be a more likely way to account for what is happening.
There's big research in Speleothem world looking at Hadley cell expansion and contraction right now. There was just a paper about a week ago over the Little Ice Age with this idea. And because when you look at Australia and Indonesia and China, and they're trying to explain that by changes in the intertropical convergence zone, well, when they're both wet at the same time, that doesn't work because the intertropical convergence zone is going to make one area wetter or drier. But if the Hadley cell expands, you can actually get both areas wet at the same time. And so that idea of sort of an expansion of Hadley cell patterns, of course, would propagate and change essentially the blocking patterns and those types of things. We'd probably have to get that through some modeling, I would imagine. But yeah, I mean, so I think that broadly this does reflect the NAO here because it drives the wintertime precipitation, but obviously it's much more than that. The main thing is that I was really skeptical of that 400-year persistence of the NAO. And I want to look at some other records from the region to see if you can hang your hat on that idea.
I'll stop there.
Oh, and thanks, Alan. Okay, so we have a break for about 15 minutes. We'll reconvene at 2:50.